Hi everyone, welcome to my channel PyproAI. So today we are going to break down one of the most important concepts in machine learning, gradient descent. Whether you are a beginner or someone brushing up your concepts, by the end of this video, you will understand what gradient descendant is. So we'll understand why we use it and how it works mathematically, and we will even implement it in Python step by step. So stay with me, guys, and let's learn. So before we even talk about gradient descent, let's understand the problem it is solving. Think about this. So, whenever we build a machine learning model like linear regression or neural networks, our main goal is simple. We want our predictions to be as close as possible to actual answers, right? So, but how do we measure how good or bad our model is? That's where a loss function comes into picture. For example, in linear regression, we often use something called mean square error. It simply takes the difference between the practical values and the actual values, squares it, and averages it. The smaller this value, the better our model, right? So we'll talk about this in this video. So the big question is, how do we find the best parameters for our model that minimize this error? And that's exactly the job of gradient descent. Let's look into it. So now let's think about an analogy that you are standing on a hill and fog came out of nowhere and you can't able to see anything at all. But you wanna get down to the hill, I mean to the bottom of the hill or valley. So what will you do? So here's what you can do, right? So well, you can look at the slope beneath your feet. If it's sloping down to the left, you take step left. If it's sloping down to the right, you take a step right. And you repeat this again and again and evaluate. So you will reach the bottom. So this is exactly how gradient descent works. So at every step, it looks at the slope of the function and it moves in the opposite direction of the slope. And slowly it gets closer and closer to the lowest point, which is the minimum of the function. So in machine learning, that minimum corresponds to the best parameter, the value that give the smallest error. So mean square error. So before that, let's talk about the error. So error is nothing but the difference between predicted value and actual value. So we consider the predicted value and compare with the actual value, and that will be the error. So when it comes to the formula, let's consider four such errors: E1, E2, E3, and E4, and the equation is given by E1 square plus E2 square plus E3 square plus E4 square divided by 4. Now let's go deep into getting the formulas and equations. So first let's consider this line equation and y is equal to slope into x plus intercept. So this is a basic math that everyone knows, right? So let's get into it. So let's just take a practical example as shown here. Rise, I mean the relation between rise and time. It can be rise of height with respect to time or money with respect to time. So let's use this equation. So now let's take an example of exact equation, that is y is equal to 0.64 and 0.45. These are the exact equation that we take as an example, and these are the corresponding values for x equal to 1, 2, 3, and 4. So now let's estimate least square error for slope, and we consider 0.56 as some example or a random number that we take, and we now put different intercept values as 0, 1, 2, 3, and find corresponding least square errors for corresponding intercepts. Now, by considering intercept as 0, 1, 2, and 3, so I have given you the values for the equation y is equal to intercept as 0.56 into x. So this will be the corresponding equations, I mean the values that you get for each and every intercept. So let's just keep a note of this value. So now let's take intercept equal to 0 and values as shown and compare with the actual values. So E1 will be 0.56 minus 1.09 predicted value minus actual value, and we'll do this for all the four errors. So let's take this four errors and try to find mean square error. So this is the formula as we discussed in this video, and after calculation we'll get this error for intercept equal to 0. So now let's take intercept equal to 0 and values as shown and compare with the actual values. So E1 will be 0.56 minus 1.09 predicted value minus actual value, and we'll do this for all the four errors. So let's take this four errors and try to find mean square error. So this is the formula as we discussed in this video, and after calculation we'll get this error for intercept equal to 0. And by the way, this is the main part of the video because we our main intention is to get minimum error. I mean that this error should be as minimum as possible for us to get a predicted value that is nearly equal to actual value. So this error needs to be very minimum. That's our main goal is. So great guys, so here's the main part. So I have calculated the errors for the corresponding intercepts, that is 0, 1, 2, 3, and I recommend you guys to use the calculators and find out these values. And let me explain you how to, I mean how, what are all the uses of these errors. So in intercept equal to 0 we get error equal to somewhat minimum compared to others, right? So this is what we are mainly looking forward, like we errors get increased whenever the intercept get increased, right? So let me try to explain this analogy using a graph, then you can able to understand why these errors are coming like this. So just by taking these four interrupts we can't able to judge about the errors. So let's try to build a graph first and try to analyze. So let's put a point on the coordinates, and as you can see I have put the points for all the interrupts and errors, and let's try to draw an imaginary line. And as you can see there is a minimum error at interrupt equal to 0 and error get increasing at every interrupt goes, if every interrupt goes on increasing. So as you can see the errors, we what we really want is that to error to be very minimal. So interrupt 0 is ideally what we consider uh, so that the model can predict value to its actual value. So actually this is not the exact graph. We to get an exact graph we need to calculate for quite a lot of intercept points, and we'll get to know what exact graph is. And let me show you the graph, exact graph what I am talking about. So this is the graph that I have been talking about, and in this graph you can see that we get a big U structure, and this U structure is mainly uh, you get this U by calculating errors for more intercepts. So by looking at this graph, we can able to see a curve, a sharp curve, I guess, at the bottom, and this is the area that we are interested in. We get minimum errors here. So what we are trying to do is we are trying to find slope that is equal to 0, so almost equal to 0. So this by finding derivative with respect to intercept for the function that is mean squared function. If you find derivative for this function with respect to intercept we get slope, and we are ideally trying to find slope that is equal to 0. Let me show you how it is done. So now to calculate the slope, of course we need some numerical values to calculate, right? So let's take the numerical values that we previously encountered and found the, yeah, uh, what do we say, practical values. So for intercept 0, we have got this, and for the expected value, sorry, the exact value, we got the following output, right? So now let's take the sum of square residual. It is as shown here, and to find the slope we need to derive the sum of square residual with the intercept. So I think most of the people know how to do differentiation by now, and this differentiation is also known as chain rule, where you need to differentiate each and every term to get the final derivative of the sum of square residual. So let's see how we can do this. So now let's take y is equal to a minus x plus b whole square. So here x is a variable as shown in the sum of square residual. So we consider intercept as equivalent to x. So if we differentiate y with respect to x, so this is what we would get, right? So 2 into a minus x plus b whole bracket. So this is what we get. So we'll apply this to the to this sum of square residual. So when we do that, we get differentiation. I mean, if we do differentiation with respect to intercept, so this is what we get, right? 2 into 1.09 minus intercept plus 0.56 into 1. So this is exactly what we did, right? So we differentiate to every term, and that will be the equivalent value to this differentiation of sum of square residual with respect to intercept. So after this formula, let's see. So now let's try to find out the slope for intercept equal to 0. That because that's where we got very, uh, I mean the lowest error, right? So let's try to find the slope at intercept equal to 0, and after calculation we get 4.74. So that's what we are trying to do is we are trying to find the slope that is nearly equal to 0, and we do this for more than for more intercepts, so that we can able to find slope equal to 0. And I really want to discuss another one topic, that is learning step that is very important. Let me show you how. What is it? So now, if we want to give a perfect formula for gradient, so we need to know what learning rate is. So let's talk about the most tricky part of gradient descent, the learning rate. The learning rate is like the size of the step we take when going downhill. So if the learning rate is too small, the steps are teeny. So you all reach the bottom, but it will take forever. So if the learning rate is too large, you will overshoot the valley. You might become bounce back on fourth and never settle. What I would like to say is, if the slope is high, and if you try to, I mean, if you try to keep the learning rate at high at every point, definitely you will be overshoot. Like you won't get any proper values, or the errors will be always maximum, and you can't able to get a perfect low errors at all. So as you can see, the green mark is where the stage where the learning rate will be high, and the white mark will where the learning rate will be low. And if the learning rate is just right, you will reach the minimum shortly and quickly. So in practice, choose the learning rate is super important. So too high or too low, and your model won't train properly. So learning rate is really very important. So after learning about the learning rate, so let's try to see how the step size is varied to predict next intercept value accordingly. So you all agree that whenever we come to the lowest point, we'll get the slope at almost equal to 0, I guess. Yes, right. So we might that's what when we get to the lowest point, we get sorry, slope value as 0, and the new step size will be uh, somewhat nearly equal to 0 into learning rate, so which is uh, very low, right? So that's why we can see that the white x marks are so close to each other. So when it comes to green mark, the slope is high, so slope into learning rate will be somewhat, it has some value, and the new intercept will be, so old intercept minus some value. So that's why we can able to see a huge difference in uh, higher slope regions. So it is very important to set a learning rate, because if we set somewhat high, even at the lower, what do we say, at the even at the lower, or whenever the slope is almost equal to zero, you might get a big value that might increase the step size, and it will cause a overshoot and you won't get an exact value. So setting a perfect learning rate is really very important to optimize our code. So now it's the math part, right? So now let's bring in a little math, but don't worry, I will keep it simple. Suppose we have a function j of theta, which is our cost function. So don't get confused. Our goal is to find the value of theta that minimize j. I mean, that's what we are practically doing, right? So theta mu will be equal to theta whole minus alpha dot derivative of j with respect to theta. So yeah, theta is our parameter. It can be slope or intercept. Here I took theta as intercept, but you can also take slope as an parameter and you can calculate it. But you have to do some sort of changes in the in performing some calculations. So j is the cost function and the error we want to reduce. So the practical derivative tells us the slope at the current point. So and one more important point is learning rate. So alpha will be our learning rate that controls our big how big our steps are. So that's what learning rate is, one key point to know what we are doing. So and it is also very important to optimize our code, right? So we subtract because we want to go downhill in the opposite direction of the slope, not up the hill. Okay, we want a minimum value. So in each step, we update our parameter and eventually we reach the point where the slope becomes zero, which is the minimum. So I think this is helpful. This explanation might uh, answer all of your doubts. So let's just continue. So of course, there are several types of gradient descent, right? So you might be thinking, do we always use all the data at once to calculate these steps, right? So the answer is no. So there are mainly three types of gradient descent, that is batch gradient descent. Here we use the entire data to calculate the gradient. It's very accurate, but if you have millions of samples, it becomes very slow. So basically, if you have a very small data set, you can use this, but when you have millions of samples, it's very difficult because it takes a lot of time. So another one is stochastic gradient descent, SGD. It's a short form. So yes, so here we use just one random data point at a time. So this make it very fast, but the updates are noisy. The cost function will bounce around but eventually find the minimum, and you might find the minimum or you might not find the minimum, but it is somewhat faster compared to other types of gradient descent. So another one is mini batch gradient descent. So this is most popular one. Instead of using all data or just one point, we use small groups of data called batches. So this gives a nice balance between speed and stability. So we just make some batches to the data that we get. It's coding time. Let's start. So let's start with the coding part, shall we? So I'm using Google Colab, and if you guys are new to Google Colab, I will put a link in the description and go to that link, and that video will definitely help you understand what Google Colab is and how it is used. So if you already know Google Colab, so let's just continue. If not, go to the description. you will get to know. Don't worry guys, Google Colab is not that complicated, it's very simple, very simple. So now let's just start with the coding part. I'm going to use two libraries. I'm using Python because when it comes to AI and machine learning, Python is one of the biggest and important programming language that you need to know. So import NumPy as NP, and I'm just going to use two libraries, Matplotlib and NumPy. Uh, Matplotlib dot PyproAI. Yeah. So these are the two libraries. Don't worry guys, if you are new to NumPy and Matplotlib, I will make a short video on it, and that video will definitely help you guys to learn NumPy and Matplotlib. So let's get started actually. So uh, now let's just create a function x squared plus 5 because I will create a gradient descent for the function x squared plus 5 or plus 7 something. Okay, so df f of x, sorry, let me define a function f of x equal to x squared plus 5. So you can use different functions also, but let's just use anyone. So d of f of x return x squared plus 5. So that's it. I have created a function. First I need to run this and run this. So and also we need to declare a function of derivative of this function. So let me give that name of the function as just derivative of f of x is equal to 2x. So that's what derivative of x squared plus y is 2x, and this is a basic differentiation that everyone needs to know. So let me make it as grad ent as x and return and return x equal to x, not more. That's it. I think we have done with the two parts. Another important step is one second. What is this? Another important step is we need to declare gradient parameters. So first, let us give a starting point as 10 and alpha as 0.1. This will be the learning rate. So as a beginner, always keep 0.1 as a learning rate or 0.01 if that is known, because choosing a perfect learning length learning rate is it's very difficult, but with a lot of experience you will get to know what exactly the alpha is, I mean the learning rate you can put for a model is. So now let's just as a basic, let's just keep it as 0.1 and let's just keep epoch as 50. just box. So epochs basically is I'm iterating 50 times. I mean I'm creating 50 steps, down steps from 10 from x equal to 10 with a learning rate of 0.1. So next step is to create a gradient function, code it for in sorry, for I in range of epochs. It is slow by the way. So grad equal to we are just giving the differentiated output to the grad, and that's what new value of x is. I mean new value of gradient is equal to more value of gradient minus learning rate, that is alpha into this grad, right? So derivative of the uh, loss function. So this will be the loss function. Remember guys, I have not talked much about loss functions. This is the loss function that we are giving. So now I will, okay, now I need to create a graph, right? So let me just give another empty array history, and I will update every value of x here. History dot append x. Yes. So let's just run this one and this one. Done. Everything's good. So now let's just plot, give the final result. Final result. The code part is print minimum x equal to x. So whatever the value that we are going to get, f of x equal to that. So just print this. Yes, we got minimum x is equal to 0.01427 and f of x is equal to 5.00. So I think we got the very lowest value that possibly we can. So now let's just create a plot. I mean let's just plot a graph or plot the path of descent. Right. So this is here you will get to know what exactly learning rate will do, and what exactly epochs is, and even the stat point. So now let's declare line space as p dot interface from minus 20 to 20, sorry, minus 12 to 20. I guess that's enough. I guess 20, yeah, that's enough to y equal to f of x. Now that's correct. So plt dot plot not capital X comma y. mobile comma label as the function. Guys, we'll get the code for this. I mean, this code in the description. So don't worry. You can play with this code as much as you want. Label equal to. Now that's good. Now plt dot scatter plot. Let's give a scatter plot. I mean scatter. So we'll print history for f of h of h for h in history. So this will be x, this will be y. Sorry, this will be y, this will be x. Which one it is? Let's see. Color, we'll make it as red, and we will label it as descent step. No, that's about the scatter, and label x label, y label, f of x, and we'll enable legend and dot title as gradient x square plus pi. Plt dot show. I think this is correct. Yeah. We can also start from -10, and you will get like this. So as you can see, the in this graph, you can see when the slope is high, you can able to see the step size is very high, and when it comes to uh, slope at very low, I mean slope nearly equal to 0, you can see step size is very low, and this is what gradient descent does, and it will try to find the minimum error and uh, try to predict the value to the actual value. So let's try to play with the alpha value learning rate 0.1, and let's just see. So you're getting -3 because you need to notice the epoch as well. So that's what, if you try to decrease the, what do you say, the learning rate, you need to increase epoch size also is increased to 100. Some that's what you're getting closer to the zero value. This increased to 500. Now we are coming to the minimum value. So that's what if you are doing very low, what do we say, learning rate, you need to increase the iterations. If you are giving somewhat okay, 0.1 learning rate, or if you have high learning rate, you need to give less outputs. So that's how it related, but it's all about experience. So when you get a lot of experience doing coding with gradient descent functions, you will get to know what exactly the alpha and fx value should be. And also, you can start from anywhere also. Three, wait a second. Just run them now. See, so you start from 3 and you got what? X equal to 1.05 to be nice. So that's it, guys. That's it from my side, and